Hello everyone, welcome back to lecture. From the previous lecture, section 8.1, we covered the basics of hypothesis testing, and I'm sure that there's a lot of confusion with it. It takes some time and a lot of practice to get this stuff correct. But what we'll do this time is actually start working through a class of problems, and then each section will go through a different class of problems. It'll be the same structure. We'll be doing hypothesis testing, but each one we have to pick out what we're given from the information and then apply the correct procedure. Okay. So in this one, 8.2, this is hypothesis test for a population mean. And in this case, we're going to know what the population, that's sigma, so that's the population standard deviation. We're going to know what that is, and that's going to tell us, that's going to enable us to pick which formula, which way we go forward. Okay. So here's what we're going to do is we're going to do basically cover some hypothesis tests. There's two ways to perform a hypothesis test. Both methods produce the same results. And in hypothesis testing, what we're concerned with is that someone makes a claim about a population statistic. In this case, it's going to be, when we're going to start out with 8.2, it's the population mean. What we're going to do is set up two statements, the null hypothesis and then the alternate hypothesis. We're going to go take a sample. We're going to determine the sample statistic and go from there. We're going to basically be able to either support or fail to support the null hypothesis. Okay, so two methods, critical value method and the p-value method. The critical value method is what I recommend always going through, even though you may deliver the p-value, the results from the p-value. The critical value helps you build the structure, get everything right, and you can kind of tell if you're correct on the p-value or not. So I recommend doing the critical value method always. Okay. So in a hypothesis test, the idea is to select a sample, calculate a statistic such as x bar, and compare it to the value in a null hypothesis H0. And again, somebody made a statement about the population parameter. We're going to build the H0, H1 from that statement, and then we're going to compare it to a sample statistic that we've gathered. If the difference between the sample mean and the value in H0 is large, it is less likely to be due to chance, and H0 is less likely to be true. Okay, so in 8.2, we're going to make a statement about the population parameter mu, the population mean. We're going to go grab the sample statistic x bar, that's the sample mean, and based upon the H0 and the H1 from the claim, then we can go and we can either prove or disprove is basically what we're going to do. So we must determine how strong this disagreement is between the sample mean and H0. It's not that we can prove or disprove mathematically. It is more that it is most likely false or most likely true. Yeah. Okay, let's go back. So here's an example of hypothesis test. So the College Board reported in a recent year that the mean math SAT score was 515, with a standard deviation of 116. Results of an earlier study suggest that coach students should have a mean SAT score of approximately 530. A teacher who runs an online coaching program thinks that students coached by his method have a higher mean score than this. Okay. So what we're going to do is basically set up a hypothesis test to check what if the students are basically scoring better if they go through her coaching program. Okay. So first of all, we have to go through and we basically have to find out what kind of hypothesis test we're conducting. There's a statement in there that the teacher thinks that the methods have a higher mean score than the 530. So in a mathematical, you have to pull this out. What we're trying to say is that the teacher believes that the mean score for students is greater than 530, so I have to have two statements. My first is just, I'm going to write that. I want to prove or support the statement mu is greater than 530. I have to write a second statement that kind of gives the complement of that. Well, it could be greater than 530, or the mean, the population mean of those students in the program could be less than or equal to 530. The way we do the test, that less than, if we can disprove equal to 530, it actually disproves all of the less than or equal to. So it's grouped in this textbooks, they're all grouped together as mu is equal to 530. We're also taking care of all the less than or equal to 530. So that's the alternate from there, but that's just a complement statement. Mu greater than 530, the complement being mu is equal to 530, less than or equal to 530, and then we have to do the hypothesis statements assignments. H0 always gets the equal version. Okay, so I just go through, I look at the two complement statements, I see which one's the equal. That's my H0 statements, that's the null hypothesis. My H1, the alternate, is the one without an equality sign. Okay, so those are my assignments. That's how I'm going to do it. I'm going to find a statement, write the statement mathematically, do a complement of that. I'm going to do my assignment of H0 and H1. H0 always gets the equality statement. H1 is the other. The H1 then will tell us what kind of test we're going to do. And there's three types of tests. I can do a single-tailed test, left-tailed test, a right-tailed test, and then a two-tailed test, which is basically an equality test. So suppose now that the teacher draws a random sample of 100 students who are planning to take the SAT, enrolls them in the online coaching program. After completing the program, their sample mean SAT score is X bar is 562. This is higher than the null hypothesis value of 530, but determine how strong the disagreement is between the sample mean and the null hypothesis of mu is equal to 530, less than or equal to 530. We calculate the value of the test statistic, which is just the z-score of the sample mean. Now remember that we're doing sampling theory, so we can't use just the z-score. We have to base it on the sample. Okay. So assuming the population standard deviation is sigma is equal to 116, we have that previous information about population standard deviation. We're going to use that in this case. And 8.3, we're not going to know what that is. We don't have that information, and we're just going to have to use the sample standard deviation. So here, assuming that the population standard deviation is sigma is equal to 116, I've got that information, I'm going to use it. The test statistic, what I'm going to compare it to, the hypothesis statement versus what we're seeing from the sample, I'm going to use that z-score. And this is based on the sample mean X bar. The z-score, this is the formula that you're going to use. It's X bar minus mu zero. The mu zero is the hypothesis statement value. So mu zero is the H0 value for the mean. Okay, and then we're going to divide that by the sampling error, the sigma divided by the square root of n. Okay, so this gives us 562 minus 530. We divide it by the 116 divided by the square root of 100. The 100 is the sample size. That gives us a z-score or test statistic of 2.76. Okay. Now all we have to do is basically say, well, how far out are we comfortable going? Okay, and then there's some standards that we'll have to look at. Okay. So here is the picture. Visually, we can see from the figure that our observed value, x bar, is equal to 562. It's pretty far out in the tail of the distribution. The 562 compares to 2.76 as a test statistic. Now remember, we always kind of, just as a general rule of thumb, if something is greater than 2 standard deviations, that's significant, right? That's kind of unusual. But we're going to do that value based on what type of test we're running and how critical we need to have that. Okay. So the critical value method is based on the idea, let me move me down just for a second, that we should reject H0, that null hypothesis, if the value of the test statistic is unusual when we assume H0 to be true. So I'm going to go back here for 1 second. So let me get back in here. Let's go back. You remember, these are our two statements. We're going to use this. The H0, the mean was the mu is equal to 530. That was our mu 0. The alternate kind of gives us the direction of the tail that we need to do. Okay, when I have the greater than, I want it the mu, and then some symbol, either greater than, less than, or not equal to, are the three variations that I can have for the alternate hypothesis. The greater than points to the right, just like if I have an arrow that's pointing to the right, that tells us that we're going to do a right tail test. Okay. So there's on the right tail, I'm going to have some critical value that I'm going to compare our test statistic to. I'm going to go ahead and do that first, do that test statistic that we compare to, and then we're just going to plot it. And if it's greater, if the z-score is in that region, the critical region, that's the rejection region, then we're going to reject H0. The stuff to the left, so anything in here, we consider that to be the rejection region. If I do my test statistic and I plot it out, comparing it to a critical value, we're going to talk about that in a minute. But if it gets in here, we reject H0. We always reject or fail to reject H0. In here, we fail to reject. So if we do a test statistic anywhere in here, then what we're comparing it against to was reasonable. Okay, but once we get it from our sample, if it's way out here, then we're going to reject. Okay. So what does that critical value depend on? Well, it depends on how, what value that we're going to compare it to. The alpha, that's our what we're going to compare it off to. In this case, one of the most commonly used is alpha is 0.05. It could be 0.01, 0.02, but 0.05 is pretty popular to use. When alpha is equal to 0.05 is used in a one-tailed test, if we do the inverse normal and find out what value of z compares to 0.05 area to the right, so that means 1 minus 0.05, let me go back, sorry, 1 minus 0.05, 0.95 to the left, that value for the z-score for the normal distribution is going to be 1.645. The case that we were working on, so for the math SAT example, we did a test statistic of 2.76. At alpha 0.05, when I get into this, the critical value, the z-score corresponding to the 0.05 to the right is z is equal to 1.645. The test statistic is 2.76. It's in that little region, that tail, that where the right tail, the left tail, depending on H1. And I went back and I said H1 right up here. The greater than, this is the tail that we're looking at, the test statistics, so we're going to reject H0. We're going to reject that those where the mean was 530. So we're rejecting the mu, the H0, but that means we're supporting H1. So if they do the program, it seems that they do an increase of their SAT scores. The average is increased. Okay, so that's how we're doing it. We conclude that the mean SAT math score for students completing the online coaching program is greater than 530. Okay, at the alpha level 0.05. Okay. So the critical values for hypothesis tests, here's the picture. The location of the critical region depends on whether the alternate hypothesis is what they're meaning it. So with the H0, that's the one with the equality. The alternate is going to be left, points to the left, or points to the right. And that's going to tell us left tail, right tail, or two tail. Here's the picture that you're going to build if I'm talking a left tail. The 0.05, so if we're doing alpha 0.05 is here, I do the Z value here, the critical. If it's to the right, 0.95 is to the left, or 0.05 is to the right. That's the critical. These two are symmetric here. Okay. Now here is if we do a two-tail test, so I'm going to compare exactly equal. Okay, the two-tail test was going to be, I want to prove that, I have a statement that the population mean is exactly 530. If it's saying exactly 530, if it's too far to the left, too far to the right, then we're going to reject H0 in both of those cases. But here what we're going to do is divide the alpha by 2. So this is the alpha over 2. So in this case, this is not the same values. This would be, if alpha was 0.05, I divided by 2, it would be the Z-score corresponding to an area of 0.025. Okay, and it all depends. So if I said 0.01 is my alpha, and if I did a two-tail test, I would do 0.01 divided by 2, 0.005 would be these values with the critical region in here. Okay. So here's some critical values and assumptions. Here you can use this instead of going back all the time and doing the inverse to give you the critical values, the Z-scores that we're going to compare against. This table is a nice table that gives you the values for if I've got a significance level alpha of 0.10, I would have a left-tailed critical region of minus 1.282. That's the Z-score. The right tail, if I'm doing a right tail, I'm going to compare it to 1.282. And if I'm doing a two-tail, remember my alpha gets divided by 2, and these are the scores we're going to use, plus or minus. So I'm going to plot those, plus or minus 1.645 on the standard normal curve, and then compare it with that test statistic. If it goes into either one of those regions, left-tailed or right-tailed, we'll reject H0. Here's the 0.05 levels, the 0.02, and then 0.01. And notice these are symmetric as long as I'm doing a left-tailed or right-tailed. They get the full 0.01 area. And if I'm doing a two-tailed, this gets divided by 2, which gives me those critical values. Now, anytime I'm using a hypothesis test and doing a Z-test, that's what we're doing here. I'm doing the Z-score. Later in 8.3, we're going to use the t-distributions, just like we did when we were doing confidence intervals. So here's the criteria for this particular test that we're talking about. We're going to do a hypothesis test about mu, the population mean, population parameter mu, which is the population mean. I know what the population standard deviation is. That's not always going to be the case. We'll talk about that in 8.3. I have a simple random sample. The sample size is large or the population is proximally normal. Okay. So here's another one. Let's do another one. Let's go through this. So the American Automobile Association reported that the mean price of a gallon of regular grade gasoline in the city of LA in July 2013 was $4.04. A recently taken simple random sample of 50 gas stations in Los Angeles had an average price of $3.99. Assume that the standard deviation of prices is 0.15. That's for all the prices in LA. Remember, when we're talking about the population, is what we are concerned with, and those are the LA prices. So it's just those. An economist is interested in determining whether the mean price is less than 4.04. Use the critical value method to perform a hypothesis test at the alpha is equal to 0.05 level of significance. So we first check the assumptions. The sample is simple random sample and the sample size is large, n greater than 30. The assumptions are met. So here's what we're going to do. The economist wants to test for mu less than 4.404. Okay. So if it's mu is equal to 4.04 or greater, that's going to be our null hypothesis. We always want to have one with an equality. He thinks that it's less than 4.04. That's the statement or the claim, but we're going to test it against the complement greater than or equal to 4.04. So here's how I would do it if I was writing it down. Here's my claim that mu is less than 4.04. My complement, mu is greater than or equal to 4.04, but when we reject the equal to, it would be rejecting all the greater than. So we're just going to leave it at this. H0 goes with the equal signs. So this is my H0 assignment, H1. Once we sign that, then we can determine what type of test we're going to do. You see this thing points to the left, less than 4.04. That says we're going to do a left tail test. It always points to the tail that we're going to do it to. So we can set everything up now. So the left tail test, we want to test this thing. It didn't tell us right here. It says use the critical value method to perform a hypothesis test at the alpha 0.05 level. Okay. So I want to go to that little table. I would suggest writing it down, putting it into your notes for your test. Here's the 0.05. I'm doing a left tail test. That's the end that it's pointing to. Minus 1.645. So I plot this, negative 1.645. There's 0 on a standard normal curve. Here's my critical value. I'm going to shade the left tail in. That's my rejection region. I usually write RR, rejection region here, point to it, critical region here, RR, rejection region. Everything in here, I write FTR right inside, fail to reject. Rejection region or fail to reject. Okay, so now all we have to do is do a test statistic. Everything, our structure is set up for us. So here was our X bar was 3.99. So here's our test statistic computation. Again, for this version, when I know sigma, the population standard deviation, and I'm doing a hypothesis test of the mean, I'm going to use this formula. X bar minus mu 0 sigma of the square root of n. The mu 0 goes with that equality, that value, the 4.04. So that's the population. What's the difference between the sample mean and the population mean? And then here's the standard error, 0.15, the sigma, population standard deviation, divided by the square root of 50 gives us the standard error. And that gives us a test statistic z-score of negative 2.36. That's our test statistic number. So here, the negative 1.64, the negatives go larger to the left. The z negative 2.36 is in that region. So we're going to reject H0. We always either reject or fail to reject H0. What was H0? That mu is equal to 4.4 or actually greater than or equal to 4.04. So rejecting that, it has to support the other one. So there is sufficient evidence to conclude at the alpha 0.05 level that the mean price of gasoline is less than 4.04. Okay. So this is a short statement. The longer statement is that we would like to include the value alpha in there so that we know what we have tested against. And that's how we say it. At the alpha 0.05 level, we can conclude that the mean price of gasoline and regular gas in Los Angeles is less than 4.04. So there's two methods. Remember I told you there was two methods, critical value method and then the p-value. The p-value is basically the probability to the left or to the right of what that test statistic value is. So I want to define, I'm still going to do the test statistic value, and then I'll just do a probability. What's the probability of it being greater than or less than that, depending on which tail we're doing, left tail, right tail, or two-tail. So the p-value is the probability that a number drawn from a distribution of the sample mean would be at an extreme or more extreme than our observed value. That's just the probability value of the test statistic. Okay. So unlike the critical value, the p-value tells us exactly how unusual the test statistic is. It gives us more of a probability value than just a z-score. Remember, they're kind of correlated. Less than 2 is unusual. Less than 3 plus or minus 3 is very unusual. The p gives you that value. So you're thinking, I'm left tail, 0.05 corresponds to the that z-score, that critical value for probability less than 0.05, greater than 0.05, or divide by 2, 0.025. Okay. So that kind of gives us the probability. Once I use the p-value, it kind of covers everything, and you don't have to worry about which tail I'm talking about, left tail, right tail, two-tail. I just give you the probability of it being more extreme. So it would be more to the right, more to the left, depending on there. Okay. The smaller the p-value, the stronger the evidence against H0. Okay. So that 0.05, the critical value, we're going to actually compare it to that. We'll get a probability value no matter what, because we're doing it against the test statistic, but then we're going to compare it against the significance level, alpha 0.05. We'll compare it directly to that, because that's what that is. Okay. So we went through, here's their online coaching program. We go through, we did the very same thing, the 530, X bar was 562. There is all of our sampling distribution, the same thing. There's our standard error. We still do the z-score the very same way. We come up with the 2.76, but now I did this. Remember this one? This one was to the right, 530. So I want to do the probability of it greater than the 2.26. What is the probability that z is greater than 2.76? It is 1 minus the probability of z being less than 2.76. Okay. So I go to my tables, my A2. I define my z-score 2.76. I find the probability, that's the probability to the left, less than that. And if I'm talking about a right tail, I want that probability out in that tail, so it's 1 minus that. That's going to be the p-value. Okay. So there's the 2.76. I go through A.2 or do our probability value, and using TI-84. The p-value, the probability of it being greater, if we did that, is 0.0029. Okay. So that's a single tail. That's a right tail, a left tail. If we have those, we're just going to present that. So the probability, the p-value, is 0.0029. Now here's the catch that we have to always remember. It depends on left-tailed, right-tailed, or two-tailed. Left tail and right tail. So the right tail is to the right, that area to the right of that test statistic. If it was a left tail test, it would be just the area to the left. So the probability of z less than the negative 2.76. If it was a two-tailed, we were doing the alpha over 2 thing, but in this case, what we do is just multiply the p-value times 2, and then that way nobody has to worry about dividing alpha divided by 2 to compare it. It's just one score that I'll always compare against alpha. Okay. So we've seen that the smaller the p-value, the stronger the evidence against H0. The smaller the p-value, the stronger the evidence against H0. That's further away. It's basically what we're doing is taking a sample, comparing it to what we thought it should be, and if it's too far away, we reject where we thought it should be. Therefore, to make a decision to reject H0 when using the p-value method, we do what? We choose a significance level alpha between 0 and 1. You're only going to do like 0.05, 0.02, 0.01. I want to have that significant level small. Compute the p-value, that's the probability of the test statistic, being more extreme, either to the right or to the left, or the twice that's out of my two-tail. But now, once I have a p-value, I compare it directly to the alpha. If the p is less than alpha, reject H0. If it's greater than, we do not reject H0. We fail to reject. Okay. If we fail to reject H0, it's kind of hard to make any kind of conclusion statements. There's insufficient evidence in either case. So if we have this, we say that H0, so if it's less than alpha, we say that H0 is rejected at the alpha level because we're comparing it, so we have to report that alpha level, still the significance level, or that the result is statistically significant at the alpha level. So here's a comparison. So usually these p-values are reported using technology. TI-84 reports them. If you're doing any large, you can get it from Excel, you can get it SAS. When you're doing any of these things and running these tests, it just gives you the p-value of the test. And then you compare it. You don't have to rerun the test if you change the alpha level. So you may want it at 0.05. And now I want it, well, what about at 0.02? And instead of rerunning it, you're just comparing it to 0.02. So here's what this is. We run a test. We get back a p-value from our software that says that the p-value is 0.0122. Do you reject H0 at the alpha 0.05 level? Is 0.0122, and we're always saying, is it smaller than the alpha? It is. 0.0122 is smaller than alpha. If it's smaller than the alpha, we reject it. So we can reject this. If this was reported by our software, we would compare it to what the current alpha that we were thinking about, and we would say, yes, this is less than that 0.05. We're further extreme. We're more extreme. The probability is less than what we were doing a cutoff. So we reject H0. What about at 0.01? We come back and your boss says, oh, well, let's check it at the 0.01. Instead of rerunning the test, this may take some time, resources. You go, no, this is actually bigger than the 0.01, so we do not reject H0. We fail to reject H0. Okay. And there's our solutions from those. Okay. So the mean height of adult men in the U.S. is 69.7 inches with a standard deviation of 3 inches. A sociologist believes that taller men may be more likely to be promoted to positions of leadership. So the mean height mu of male business executives may be greater than the mean height of the entire male population. So a simple sample of 100 male business executives has a mean height of 69.9 inches. Assume that the standard deviation of male executive height is sigma 3 inches. Can we conclude that male business executives are taller on the average than the general male population at the alpha 0.05? Okay. So basically, we're going to assume that this is the same standard deviation as here. We're going to make a statement, so we have to do some fundamental statement out of there. What are we trying to test for? I think, this is from the sociologist, that the mean height mu of male business executives are greater than the entire male population. So I would write something like mu is greater than the 69.7. That's the mean height of all the adult men. So mu greater than 69.7, and now I need a complement. Less than or equal to 69.7. All I'm really worried about is the equality, because if it's the closest distance that we're going to reject it is the equal, anything other than that. So we're going to do the 2, mu equals 69.7, and mu greater than 69.7. Okay, so we have those two statements. Here's our 69.7 statement, our greater than 69.7, and now we have to assign H0 and H1. Which one are we going to fail out of this thing? And it's always going to be rejecting or fail to reject H0. Who is H0 out of those two statements? It's the one with the equality. So that's the one that we're going to test against. The other one tells us what kind of test. Points to the right, so that says a right tail test. We're going to do a right tail test. Okay. So we did the same thing. The N is 100, our sample size, that's greater than 30, we should be good. Again, we go back, we calculate our z-score of the test statistic. The x-bar of the male executives were 69.9. The mu0, which was the H0 value of 69.7. My standard error, 0.3. The sigma over the square root of n, that's 0.3. So that gives us a test statistic z-score of 0.67. Right-tailed test, remember the greater than, the p-value to the area to the right is z.67. So if I'm doing this, if I go to the tables, I go look for 0.67, that's the area to the left. I want a right-tailed test, so I'm doing more extreme than that thing. What's the area to the right? Turns out to be 0.2514. Okay. So if I compare it against the 0.05 directly, I'm comparing the area. The probability is 0.2514 less than 0.05. No, that's a bigger area. So we do not reject the H0. What we can say is that there's insufficient evidence to support that they're greater than the executives are greater in height than what a standard, any of the average male in the U.S. Yeah. So there's not enough evidence to conclude that male executives have a greater mean height than adult males in general at the alpha 0.05, if that's what we're comparing it at. So at a large company, the attitudes of workers are regularly measured. Let me make sure I get all this stuff. Measured with a standardized test. The scores on the test range from 0 to 100, with higher scores indicating greater satisfaction with their job. The mean score overall of the company's employees was 74, with a standard deviation of sigma is equal to 8. That's our population. That's everybody that we're concerned with. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day per week working from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see whether their mean level of satisfaction had changed since the policy was put into effect. The sample mean was 76. Assume the standard deviation is still sigma is equal to 8. Can we conclude that the mean level of satisfaction is different since the policy changed at the alpha is equal to 0.05 level? So what are we comparing it against? The standard ones. So we think, can we conclude that the mean level of satisfaction is different since the policy changed at the alpha is equal to 0.05? Different is either less than or bigger than, greater than. So we're actually going to do a two-tailed test on this one. We're going to compare against equals or just not equals. Is there a difference between the two? Okay. So in this case, I'm going to compare either they're equal, the 74, they're the very same thing. Here's our statement that we think that it's probably, or is it different from that as these things have changed? Is it not equal to 74? The not equal is a two-tailed test. It could be either less than or right tail. If it gets farther enough from 74 in either direction, we don't know, then we'll know that it's different from there. Okay. So the sample value, 76, the sample mean, we're still going to use the population standard deviation. We know what this is. If we know what it is for the population in general, we're going to use that value. If we don't, we're going to have to use the sample standard deviation, and we're going to have to tweak some things in 8.3. Okay. The very same thing again, I'm going to do a test statistic. Here's kind of our critical regions, right? Here's the 0 of our standard normal. Either left-tailed, right-tailed, the two-tailed test, right? Here's left-tailed, here's still right-tailed. What we call this a two-tailed since both of them is involved. The values that we're going to do, if we're comparing at the 0.05 level, we go back to our table. Those were the negative 2.24, 2.24. Why does this change? Because these are the 0.05, 0.0, 0.0025 actually. Okay, so we go through, we set that, we've got the t value. Here's our test statistic. I'm going to do either one. So what they're saying here is the probability that it's less than. This wasn't the critical region, excuse me. This was the plotting of here's our test statistic. Here's the 2.24, the negative 2.24. Then they're going to do the area. I would do the critical regions. I would go back and say, give me the 0.05, 0.025 is what I would be looking for, the z-score here, a 0.025, negative, and then here's the positive version. And I can compare that directly. That's the critical regions. We're going to do p-values. So all I need to do is just do one of these. I would use this one and then compare it directly. But here I'm going to multiply times 2. So I've got a two-tail test. The probability that z is less than negative 0.24 is 0.0125. That's the probability in that area. But since I'm doing a two-tail to get the p-value, I multiply that times 2. That's the p-value is the 0.025. That's the half version of that, okay? So it's less than 0.05 that we're comparing against. We reject who? H0. So we conclude at the alpha 0.05 level that the mean score among employees has changed since the adoption of telecommuting. So in the TI-84 Plus, if you've got that version, this will do it for you. There's Excel will do it for you. There's several testing. But you can do this on the i84 Plus by going into the stat, highlighting the test, selecting a z-test, and then go through what you're testing against. The mu0 74, your sigma is 8. It asks you which one it is, and it asks you what the sample mean was. How many n is 80? Which test are you doing? Are you doing a left tail test? Less than mu0, greater than mu0. We're doing, in this case, the not equal, which is the two-tail test. And then we just execute the test. And it'll give you, here's the, does it give you, what's the p-value? It doesn't. Once you do that, though, it'll give you the p-value. Okay. So here's the thing again. That's what we were testing. Once we run it, here's the results of the z-test. It says p is equal to 0.02534. Notice that was twice what you would have thought if you just did it by hand. You would have the 0.0125 from each tail. So you just look, once you're doing these tests, you don't even care. Once you have a p-value, you don't care which version of the test you're running. You're just comparing it directly. At the alpha 0.05 level, you would reject H0. At the alpha 0.02 level, you would not reject it, nor O1. So there is a relationship between hypothesis test and confidence intervals. That basically says if you went in between the two, that should be, if you have a 95% confidence interval, 5% on the outside, that basically gives you these ranges that if you went and checked, if you thought it was in there. So here, if you did this and you did the 74, here's the confidence. So you based it on your sample, you built your confidence, 95% confidence interval. The true mean should be in here, but the statement was, or the hypothesis test for H0 was 74, you would reject that possibility because you're confident. It wasn't even in the confidence interval. Okay, so it's two ways of looking at the very same thing. If you do a hypothesis test with a p-value, you can kind of tweak instead of rebuilding this confidence interval with a changing alpha. Alpha, the probability of a type 1 error. Okay, it's basically from the 8.1, a type 1 error occurs if we reject H0 when it's true. So we don't know if it's true or not, but all we can do is go grab a sample and look at it and compare the values. If we reject it, we were rejecting it based on the alpha level, right? But what if that was true? If we rejected, but it was true, we come back 3 years later, 4 years later, we've got all the data. Now we can know if it's true or not. If we had rejected it, that was a type 1 error. It was true, but at that time we just had our information on the sample, we rejected it. Okay. The type 2 error occurs if we do not reject H0 when it is false. We failed to reject it, but it was false. Again, don't worry about which one it is. All we can know is later on if I tell you if it was. Okay. But we can reduce the possibility that it is a type 1 error by tweaking alpha. Okay. We reject H0 when it is true. Okay. So if we increase the H0, we're going to basically reject more H0s. If I reduce the value of alpha, I'm not going to. Okay. So the probability of a type 1 error is equal to the significance level, which is denoted by the alpha. In other words, if we perform a test at a significance level of alpha 0.05, the probability of making a type 1 error is 0.05. Because alpha is the probability of type 1 error, why don't we always choose a very small alpha? Because if we choose that, then we increase the likelihood that we get a type 2 error. They are mutually exclusive. I can't decrease both type 1 errors and type 2 errors at the same time. Okay. So that's why we kind of pick a 0.05 and just go with it. Okay. The thing that we call the type 2 error is the beta, the probability of making a type 2 error. I can't tweak both of these things. I can reduce one or the other, but not both at the same time. Always, if I'm going to do some testing, if I do, we go do a study and I do these testing, we should put both the p-value and any significance levels. If you put it in there, if we do any critical regions, here's the corresponding so that we have that. Okay. So anytime I make a statement, I want to put here's the p-value and at an alpha level so that we know what we are rejecting or fail to reject and how close they are. Right? If I had if I'm testing at alpha 0.05 and my p-value is 0.049, that's only a difference, very small. So it may get somebody's attention that, hey, this is getting pretty close. How strong is it? How strong is the result? So report the test statistic is always good to have that z-score, and you can kind of compare those. So if you want to do a critical regions, you've got that value that you can do. Here's my critical regions based on the z-score of alpha, and then I can compare it directly with the rejection region. Okay. So if you do the test statistic, you can also determine where it's in the critical region. Okay. So using the critical value method, you should report the value of the test statistic rather than simply stating whether the test statistic was in the rejection region or not. And probably here is the critical value that you're testing. So there's a thing called statistical significance. That's what we talked about. If it's very small, the probability is very, very, very small, 0.05 or less is what we're talking about, or in a two-tailed region, 0.025, that's statistically significant. I grabbed a sample that the probability of it being there is very small. Okay, but there's also a concept of practical significance, and practical significance means that this was useful information that I could go and do something about it. Okay. So for example, a new study program may raise student scores by 2 points on a 100-point scale. Okay, I go do just like we did the SAT, we go grab a sample that has a study, that the people have been on a study program, and we see that, yeah, there's a 2-point difference that makes it a statistical significance. but it's not really practical. I mean, that's not going to change your grade that much. Is it worth the money of that $500 package as a study program to get 2 points? You know, not for sure it is. Okay, so take a look at these things at the very end. You know, go through, read the book, go back through the slides by yourself. You know, it's important that you kind of pick up being able to write these hypothesis tests. Go to the end of the chapter, the problems in the end of chapters. What are you looking for? Do I know sigma? If you know sigma and then you're going to use it from the population. Give me the claim. What am I testing against? The claim, the complement. H0 goes with the equality. H1 is the other of the complement. That's the alternate hypothesis. It's going to tell you whether you're doing a right tail, a left tail, or a two-tail test. Calculate the value of the test statistic. Plot it using critical value regions, or find the probability value of that and then compare it. Okay. I hope you found that helpful. Go back through it. Take some time. We're going to do this all over again, but next time we're not going to know what the value of sigma is, the population parameter standard deviation. We're going to have to use the sample standard deviation, but that's going to modify what type test it is. We're not going to be able to use the standard normal distribution. We're going to have to use the student's t-distribution in that case, and we'll talk about that. Okay, so have a good day. Hope to find this helpful. See you next time.